epoch is 10 to the 57 grams per centimeter cube. But who worries about this state of matter? There is no discussion of what kind of matter was there, what its equation of state was. So, sometimes I am reminded of what is called this Parkinson's law, which says that committees will pass budgets of several million at a stroke without discussion. But if they had to discuss whether to spend 1,000 rupees or 2,000 rupees on bicycle shed, they will spend lot of time discussing it. So, they spend lot of time discussing this, but they pass this without any discussion at all. So, I would say the bottom line of what I have so far said, that standard cosmology presents a coherent picture in which different observations fit precisely, but it contains a lot of untested plus untestable ideas and also ignores the apparently discrepant evidence. So, in my last lecture I am going to discuss alternative cosmology. So, here I want to end up with some comment by Fred Hoyle in the Vatican Conference of 1970. He says, I think it is very unlikely that a creature evolving on this planet, the human being, is likely to possess a brain that is fully capable of understanding physics in its totality. He says that the human brain may not be able to comprehend physics totally, and I think this is inherently improbable in the first place, but even if it should be so, it is surely wildly improbable that this situation should have just been reached in the year 1970. This is because the Big Bang supporters in 1970 were telling very vehemently this is the way the universe is. So, he was cautioning that why do you think in 1970 you have understood the ultimate problem. And if you look at it now, in 1970 the standard Big Bang model did not have inflation, it did not have grand unified theory, it did not have non-baryonic dark matter, it did not have lambda, it did not have CMBR anisotropy. So many things have come after that, but the claim was being made in 1970 that now everything is understood and very little is left. So, by the same criterion, if you ask today's Big Bang cosmologists, they will say everything is understood now, a few small matters are left, exactly same what they said in 1970. So, then you point out to them, well, look, in 1970 this was the case. So, they said those people did not do their observations as accurately as we are doing today. It is precision cosmology, everything is precise and it's concordance cosmology, everybody agrees on this. Without these words, they were saying the same thing in 1970, that those people in 1930s and 40s in Hubble's time, they made a lot of mistakes, but we are doing the correct observation. So, this attitude is what I am taking objection to, is not a scientific attitude. So, my plea to the cosmologists present is the following: please recognize the rather speculative foundations of standard cosmology and allow alternative approaches to be discussed. Of course, like the standard cosmology, the alternatives should also be subjected to rigorous scrutiny. So, there are these papers and books which I here this different approach to cosmology. This book discusses the alternative cosmology, which I want to talk about in my third course and third lecture. And Introduction to Cosmology, this is a standard textbook describing mainly standard cosmology. So, you can have a look at this, and the papers I referred to in this discussion, they are given here, including Newton's earlier work, and you find other papers which are relevant to this discussion. So I think I will, this is McKellar's publications of Dominion Observatory, that is the one which talks about microwave background. So here you see the present scenario of standard model. This is the Big Bang. Then there was this quantum gravity which produced these fluctuations which led to, by inflation, finally here. And from here you make these galaxies in recognizable form. So you are looking backwards, and this is the limit up to which you can observationally see, because beyond that light gets scattered. So all this is not visible, not seeable, and the physics that you are talking about is applicable up to somewhere here, where it is inflation is already, you are in the untested physics. So all this part is neither observed nor using physics that is known. This is a present Big Bang. And this is what I call epicycles of standard cosmology. When I show this picture, the Big Bang people get very annoyed. So if there are Big Bang people here, I apologize in advance. Epicycles, as you know, the Greeks had to build epicycles to understand the position of planets at a given time, and they thought everything works in circles. So that is why circle upon circle upon circle they kept on drawing. So here, this is the standard Friedmann-Robertson-Walker model, which was predicted by Friedman. Then lambda came here, and then people began to have n-body simulations, dark matter biasing, how much is dark matter distributed with respect to visible matter. Then there is inflation. There are many kinds of inflation. Then there is quantum fluctuations. So these are all put in at different levels to understand the Big Bang. And then I had drawn this picture that there were some blind men who were sent to look at an elephant, and they gave different answers because they touched different part of the elephant. Somebody looked at the tail, and so in the same way, this is the universe that people are looking. So this person says this has a large lambda, and say, good, now here he says, from fluctuations of his years, I know that he has been free since before my time, and his body has a bias, and he's made of CDM, of course, this particular thing. So they are just symbolic things, are trying to understand the universe, and the elephant is saying, help me from this analysis. I think that is where I will stop my talk today. Thank you very much. Which finite model mean?
I mean, he assumed that there is a cosmic background which is causing the J equal to 1 rotation levels, you said.
Yes, yes. So levels of the spectroscopy of those stars showed cyanogen line occupancy. Normally, if there is no radiation, these things settle down to lowest energy level from the relative population.
To the other effects on that.
Yes. So in relation to, if you have station, will give you that e to the minus e over kt.
So the assumption of a background radiation.
You see, what you do is when you see these upper energy levels, you deduce that there must be radiation, much temperature is there. That is how they did that. Subject, in my opinion, is although very interesting and very challenging in terms of combination of two very important subjects like cosmology and particle physics. my reservation about any claims made from that kind of study is that the claim can be very speculative. It is not based on known physics or known observations. So that was the reason I was skeptical about the present work on the very early universe. At the same time, it would help if one throws out some alternative ideas in cosmology which one can compare with the mainstream Big Bang cosmology, because then one can check whether the alternatives have anything new to offer, whether they have closer connection with direct observations than the Big Bang. One can also look at the weaknesses of alternatives vis-a-vis the standard cosmology. So, in that spirit, I am now going to describe a cosmology which Fred Hoyle, Jeffrey Burbidge and I had proposed in 1993, and we have since developed it in many respects, and some of those I want to summarize here, because I am often asked by Big Bang supporters that if you are critical of Big Bang, what alternative do you have to offer? So it is always good to come up with an alternative, and it is not the claim that the alternative is free from defects. There will be defects in the alternative, shortcomings or speculations also, but one has to compare two alternatives, and that way one can make progress. So, here I want to talk about the work by Ambatsumian, an Armenian astronomer, Victor Ambatsumian, whose centenary was recently celebrated about 2 years ago. Yes, if you can turn this light off, it will look better. And Ambatsumian was of the opinion that the universe contains a number of situations where explosive creation of matter is going on, and he pointed out examples in various situations. So I have given a quotation here. One of the important problems confronting us in the study of the outflow of matter and ejections from the nuclei of galaxies is the quantitative evolution of the ejected masses. This refers equally to those galaxies of which the central parts show emission lines, and to radio galaxies, and to other examples of discrete ejections. So he was showing various parts of observational astronomy where you see matter coming out, energy coming out from a very tiny volume. So his argument was that you should look upon this as an example of creation of new matter and new energy. So one can say that he was so impressed by the data of this outflow of matter that he did not hesitate to sacrifice one of the holy cows of basic physics. So the cow is shown here. So what he says, that the few facts at our disposal show that these data may conflict with the law of conservation of energy and matter in its present form, and may perhaps require a generalization of this law. So he was willing to give up the sacrosanct law of conservation of matter and energy in face of the evidence of this outflow or creation of matter. So just to give you examples, here I have the famous interacting galaxy pair 3561A and B, the plate is produced with the kind permission of these two people, Duo and Mirabel. Many years ago, Ambarsumian gave this as an example of a galaxy in the process of ejecting a new galaxy. So, here this thing and the jet-like thing coming out. A high redshift quasar very close to this pair is marked by an arrow, which you see in the picture, while we, that is Hoyle and Burbidge and myself, and Ambarsumian believe that this is an excellent example of one galaxy ejecting another. The people who took the photograph believe that it is one galaxy disrupting another. So, you already got two galaxies and there is a tidal interaction. So, this to them is an example of a violent merger. That means that they think it is a case of merging galaxies. Now, we believe that the existence of much star formation and the high redshift quasar shows that creation process is at work. There is exceptional situation taking place. So, what I want to emphasize here is that the same picture can lead to different interpretations, and one needs sometimes more detailed astronomical study like spectroscopy and so on to decide what is right. So, the alternative cosmology, which we have based on Ambarsumian's ideas of creation of matter in small pockets, was proposed in 1993, and it was called the quasi-steady state cosmology, QSSC, and the reference is given there in FJ. So, since then several publications on this cosmology have appeared in various astronomy journals as well as physics journals and conference proceedings, and in particular we summarized in the year 2000, we summarized the work of those 7 years in this book, Different Approach to Cosmology, and after this also some papers have come and I will refer to them, but if you want to have a consolidated account as to why we do not like Big Bang and why we propose alternative, this book will serve the purpose. So, what is the quasi-steady state cosmology? What are its parameters and its epicycles? You remember I had epicycles of standard cosmology. So, what are here? How does it explain the present phenomena of relevance to cosmology? What new predictions does it make that distinguish it from the standard Big Bang cosmology? So, to answer these questions, I will first give you some basic features of this cosmology. So, and the underlying field theory is a theory of gravity which Hoyle and I had proposed around 1964, and this was based on Mach's principle and leads to gravitational equations similar to general relativity, but with the addition of a scalar field. And you see here the field equations described. You have got this thing plus lambda g I k 8 pi g t I k minus this is the scalar field C, whose gradient is C I, and F is positive. So, you have got a negative energy, negative pressure kind of field here, and lambda is also there. So, let me say a few things about it. The cosmological constant in this theory originates from the inertial interaction between particles in the universe as a whole. So, it has a Machian origin and has the right order of magnitude. If you take the universe as given by a Hubble constant that we measure today, then one finds that the lambda comes out to be of this order. So, this is of the right order. There is no problem of a sudden drop in the value of lambda as in the inflation, but the difference is that the cosmological constant is negative. That means it is not a cosmic repulsive force, but cosmic attractive force. So, how does this whole thing work? We will see very shortly. You might think that I mean, the moment I say cosmological constant is negative, people immediately say, so you will be in disagreement with supernova measurements. So, I want to come to that later. So, the C field terms arise from the inertial contributions at the ends of world lines of particles and describe the dynamics of creation. For example, one arrives at the typical created particle of Planck mass. So, one can ask what is the particle created in this process, and that mass can only come out of these numbers which we have in our theory, h cross g and c. There is no other number. So, Planck mass will come out, which has an energy 10 to the 22 GeV. So, the 10 to the 19 GeV. The creation of matter, the action principle from which the above field equations are derived, requires the endpoint condition to be satisfied at the creation of matter. That means, the momentum must be equal to, momentum of the particle created must be equal to the gradient of the C field. So, you get this condition, square of the momentum, that is the rest mass square, is equal to the square of gradient of the C field. So, this must be satisfied. So, one can argue that the Planck mass is a very large mass compared to the other elementary particles, and so if you want to create particles which of that mass, you cannot normally do it in any point in space time where the expected strength of the C field as measured by its gradient is very moderate. So, where can you create matter? Because that condition must be satisfied. So, you can create it if you are in a region where the gravitational field is very high, which, as you will shortly see, raises the strength of the C field. So, one could say except near massive objects, this condition is not satisfied, massive and collapsed compact objects, because as you will see here, if you take an object of mass m and radius r, then the CL you see here is plotted against the Schwarzschild coordinate, and this declines like this. That, or to put it the other way, if as you go closer to the object, it rises, and this is the Planck mass line which it must attain. So, what it means is that if you are close enough to the so called event horizon of that object, Schwarzschild radius, that is 2 gm over c square, then you are able to create a particle there. So, the question is, do you have such particles? So, the answer is yes, if particles which are close enough to becoming black hole, but are not yet black holes, would have this kind of possibility. So, one needs a near black hole type object to serve as a nucleating source. So, near such a mass that is close to the Schwarzschild radius, there is creation of new matter, and the negative energy C field also is created at the same time, and the result is that the space time expands as a result of the negative energy field. It is a feedback on the space time through equations, and the result is that if there is a lot of creation of matter, that matter is ejected outwards in a local expansion. So, it is blown outwards, and this is what we called a mini creation event or an explosive creation of matter, and this is what Ambartsumian had been referring to as the creation of matter in a explosive form. So, what you need for this is a compact object very close to a black hole, but not exactly a black hole, and also producing enough matter around it to create an explosive C field which blows it out. So, the point I want to make is that in this explosion there is no space time singularity, because nowhere has we reached that r equal to 0 in this. In fact, these near black holes, one can show that if there is C field present and the collapsing object bounces, and therefore you get a finite radius, minimum radius, and so no singularity is there. So, the purpose of this event in cosmology is that if you have so many such events taking place everywhere, there will be local explosions, and the combination of all of these would, if they can harmonize, would be to produce a large scale explosion or expansion of the universe. So, it is proposed that the universe is driven by such mini bangs rather than a singular once for only Big Bang in the standard cosmology. So, we can see how do we apply to cosmology. The simplest such model would be the steady state model, in which steady creation activity will drive the universe to an ever expanding mode with an exponential time scale factor T over P. This is what the solution of those field equations would give in the simplest case. But a more realistic model has the universe expanding with a long term steady state factor together with oscillatory modes, which is going around that long term steady state. Oscillatory mode come from phases of expansion and contraction. So, how does this happen? So, let us see how the expansion, let us suppose the universe is locally expanding. Now, when it expands without creation of matter, then there is a dilution of the C field, and when the dilution occurs, the creation centers, where that is these near black hole like objects, if the overall presence of the C field is becomes lower and lower, in order to create matter you have to raise that above the threshold, and that means your creation activity becomes less and less frequent, and it dies down and stops. And what happens is, as this thing stops, the expansion slows down, and because there is a negative lambda, it begins to contract. The effect of the lambda being negative is seen here, that it makes the universe contract. So, in the contracting phase, what will happen is that the C field strength will build up because it is compressed, and when it is built up, the creation centers become more and more active, which had died out first, they start becoming more active, more effective, and the contraction slows down then, because the repulsive nature of the C field generated in the new creation center will stop the contraction, and the whole thing will start expanding again. So, you see here this whole cycle has a feedback nature from creation field and lambda. So, one can combine this effect to say that you can get a solution of this kind. The scale factor is proportional to the exponential T over P times an oscillatory T over Q. That is, the expansion, long term expansion has a time scale P, and short term oscillation has time scale Q, and there is an eta here which is lying between 0 and 1, but is not equal to 1 because there is no singularity. So, S of t never becomes 0. Now, when this happens, you can ask what are the parameters of this model, and you see here there are 3 parameters P, Q and eta, and one has to ask how can one determine this, and if you determine this, do they then freeze the model to that particular form? So, the answer is yes, this is the quasi-steady state cosmology, and typically if we want to fit to present data of large scale structure of the universe, the Q has to be around 50 gigayears, P around 1000 gigayears, and eta around 0.8. Now, these numbers are indicative, it is not, they are not frozen. So, we are not claiming a precision cosmology where these parameters are precisely fixed, but it is of this order. And we can see how the expansion is, these are expansion and contraction, but there is a long term rise as you see, which is the indicated by P, and we are somewhere here. So, if we are here, we still have some expansion in ahead, later on it will contract, and if we look in the past, there was this contraction in the previous cycle. So, if we see some object from this part here, from here, then that object will show blue shift. So, this is a kind of difference between the standard cosmology. All these points will show red shift, from here up to here you will see red shift, and this part will show blue shift. I will come back to that later. So, we compare with observations, and first of all it was incorporated, it has incorporated Ambatsumian's idea of mini creation events or mini banks. So, one can see that already in the way I introduced it, and the kind of mini creation events that we can apply it to are the gamma ray bursts as you see here, then radio jets, then active galactic nuclei, and even origins of clusters, because Ambatsumian felt that the dark matter argument requires a thermodynamically balanced cluster, but if the cluster is not thermodynamically in equilibrium, then it could expand, and if these clusters have this expanding tendency, then they may have themselves originated from an explosion. So, these are the ideas, and structure formation, we had worked on the idea that each existing galaxy might have by probability a neighbor created through explosion in its vicinity, and one can then create an n-body problem or n-body calculation, where you take a million points which are distributed here on this, you can take a square shape, and first you distribute randomly million points. Here you see 100,000, but what you do is take a cube, and in the cube you distribute a million, and you take slices, and the slices will contain of the order of 100,000, and you produce one by random numbers, you select a few of them and create new matter, new point around it, and you expand it as per the expansion of the universe. So, what happens is that your original square has become bigger and it has more points. So, the number density of points is still the same. So, you take an inner square of original size and you are back to where you were, but now you have gone through one cycle of creation. Then you produce this again, create another neighbor, and you go on doing this. So, what you find, as you see here, there are clusters and voids. That means you see gaps and matter distribution, and here is the 2-point correlation function that you find, and you find after about 8 or 10 iterations you get the 2-point correlation function that is normally observed for cluster galaxies. So, you see a very simple argument. I mean, we didn't have to do a very large or sophisticated n-body calculation, but it is done through introduction of creation of matter, and we have been able to produce essentially the slope minus 1.8 of the 2-point correlation function that is observed. Of course, we need to polish it up more by putting some gravitational effect of clustering, but we feel that this indicates a generally correct approach in the present cosmology. Then the thing that one has to understand in this cosmology, because remember there is no Big Bang, no hot era. So, how do we understand cosmic microwave background? So, one has to think of a completely new scenario, and the scenario is that CMBR is relic starlight left over from previous cycles. So, you had stars in previous cycles, they are born and 50 giga-years is long enough for a star to run through its whole life cycle. Even the lower mass stars will also be burnt out. Then new matter is created at the beginning of each cycle and new stars are born. So, this process goes on, and you begin to ask the question, what happened to the radiation emitted by all those stars in the past? So, that radiation must be pulled together from minus infinity to present, and one has to ask at that present epoch what will be its energy density. So, what happens is that if one looks at the star for a star burning process at present, we get the stellar activity that is around, and one can extrapolate from this, and one gets the 4.10 to the minus 13 or centimeter cube energy density at present, which corresponds to 2.7 K. Now, I had mentioned in the context of the old steady state theory the argument of gold, which produced a similar answer, and that required greater star forming activity in the past. Now, in this particular cosmology, you don't require that, but you have the previous cycles, all of them contributing. And you can ask, isn't that infinite number of cycles, because the universe has no beginning, wouldn't you get into an infinity of answer? That is the, will you get a divergent answer? The answer is no, there is an e to the minus t over p factor. So, that produces convergent and a finite answer. So, you end up by getting this finite value which I have shown. So, the question now is which in gold could not answer, and which is why Bondi and Hoyle said we will not publish it in that form, but what is the thermalizing agency? How is the radiation thermalized? So, the answer is that when you form metals in stars, they are ejected from supernovae, and they are ejected in the form of very high temperature, so vapor, metal vapors. And it has been observed from laboratory experiments that metallic vapors condense not as balls or spherical particles of metal, but as long threads. So, this is an observed fact and not a conjecture. So, you get whisker shaped particles in the vicinity of supernovae, and supernovae explode, so they drive these things out of the galaxy into the intergalactic space. So, you ask for the dust made up of intergalactic dust made up of such whiskers, and you look for the absorption properties of this dust with wavelength, and you see that it declines at long wavelength like radio wavelength, but it rises and is more effective at millimeter wavelength. So, where you expect to see the peak of microwave background, that is where the dusts are more effective dust particles of this metal whisker form, and typically you see that you need a intergalactic density of 10 to the minus 35 to 10 to the minus 34 grams per centimeter cube to make to be effectively to effectively thermalize the starlight which was present from the past. So, if you look at how much is the density of iron or metals in the universe, you find that this is a few percent or less than whatever the metal is overall produced. So, you therefore have no problem of producing this kind of dust for thermalization. And the contributions from the latest star clusters of the present cycle, this has not yet had time to thermalize. So, they will appear as minor fluctuations to the microwave background thermalized black body curve. So, the power spectrum of such inhomogeneities has been computed, and this is what we find in the quasi steady state cosmology, this power spectrum. Now, this one is the most dominant power spectrum peak, that is the what's called a boomerang peak, and that in the standard cosmology arises from what happened the oscillations, plasma oscillations which occurred in the before the last scattering surface. So, people ask us how do you get this peak if you didn't have that last scattering surface or plasma oscillations of that temperature. So, the answer is here what happens is the starlight is being thermalized, and thermalization will produce some patchiness because there are clusters of galaxies. Where there is cluster, there will be more radiation. Where there are voids between clusters, there will be less radiation. So, you will see a fluctuation of the characteristic size of a cluster. So, you ask yourself at the last minimum of your oscillation, you remember there was this curve here and we were somewhere here. So, at the last minimum, redshift was of the order of 6 to 7. At those redshifts, if you had clusters present, what would be the characteristic angle subtended by them at us? That will be the angular size of fluctuation, and that would translate into the value of L, and that L equal to 200 comes from that. So, it is not coming from plasma oscillations, but it is coming from the typical cluster size subtending an angle. Now, a weaker effect would be if you have groups of galaxies which will subtend a smaller angle, and therefore, it will be larger value of L. So, this peak will come like this, and then there is a third peak which come from individual galaxies. So, you get peaks coming into this power spectrum of microwave background, and we managed to fit it to the observations. And what I want to say here is that the red and blue are Big Bang and the quasi steady state put together. Blue are the Big Bang and these are the quasi steady state, and you can do some kind of chi-square analysis and show that the chi-square is acceptable in the quasi steady state case, although it is not as good as in the Big Bang case, but statistically it is acceptable fit. So, it would be interesting to see further whether we can go on comparing in when the next satellite based data comes in. Now, we come to the redshift magnitude relation for supernovae, And you might say that with the lambda term negative we will not get the right answer. The answer is actually because of the whisker dust, the distant supernovae get dimmer, and the amount of and what we did was we took the density of dust as a free parameter and said what for best fit to supernovae data, what do we get for the density of the dust. So this can be done, and we find that the density lies in the same range as was needed for microwave background thermalization. So this is in a way a vindication that the same process is working for two different effects, and we didn't have to fit one to the other, one value for one and the other for the second. So there is some confidence that the effect may be correct. That is what I have said here. The dust density as a free parameter, we can work out the best fit curve, and one gets a fit comparable to the best fit Big Bang model, and for a density that is consistent with the density required for CMBR thermalization. Then the next thing that may be of interest to gravitational wave detectors, if you have mini creation events, they can be very powerful emitters of gravity waves if they are non-symmetric, spherically symmetric. And as you saw, some of them are linear and jet-like, and if there is a rotation, the idea is that if you have a curve type of object, curve black hole type, near black hole type, then it will produce creation matter along the polar axis, because that is the point along which it can escape most easily. So you can get mini creation event generating gravitational waves, and the expected peak effect is not in the optimum range of LIGO and other observatories, but even then it may be detectable, and we have done some calculation and found that this particular paper, those who are interested in gravitational wave analysis, you will find on that this paper discusses possible physical sources which one should look at with the new generation of gravity wave detectors. So the conclusion to which I come to in this whole process, that cosmology is still an open subject and there is need for some independent thinking rather than just take one cosmology only. And we like to show a picture which is present given in our book also, different approach to cosmology. You see a flock of birds and they are all going in one direction, and this is characteristic of present situation in cosmology, where everybody is going in one direction. If you look carefully, you see some things that people are going in the opposite direction. So there are a handful of people like us who are going in the opposite direction. But the point is that one needs to keep the alternatives in mind. It may not be a very perfect alternative, but an alternative all the same, and this is the reason why I would like to end at this stage. Thank you very much. Any questions will be welcome.
There are no black holes in this field.
No black hole. Objects which go close to black hole then bounce. No singularities also.
So then you come against all this evidence and supermassive black holes.
Yeah, when people say, astronomers say that they have seen a black hole in the center of the galaxy, what they have really seen is an object which is compact, and its strong gravity is producing concentration of stars or movement of stars. So these objects.
Gravity, like if you have large enough gravity, it will, that you can see these oscillations.
Yeah, well, one could motions are more easy to see because the photons are those phenomena that you see are the outward motions, interpreted as the inward cause of the oscillation. but but there are oscillations in stars which are seen. So I do not have a specific example which will
Continuous for 3, 4, 5 years.
yes.
There, if your central object has changed, it has expanded or contracted, you're going out.
Yeah, one could, if such oscillatory objects exist, then gravitational waves should show some kind of oscillation.
With a very long simple,
Yeah.
7, 8 years. Masses.
Yeah.
Of two sources.
Yes. For a given type of detector, what is
This long range variation, which is of the exponential nature.
yes.
And suppose I want to extrapolate into the past. So what is the physically meaningful?
It would be a characteristic of exponential. So you will not ever reach t. It restores it back to the same stage. So I don't expect any physical difference as you go.
Doesn't have any.
Yeah, t equal to minus infinity means essentially the universe had no beginning, because there is no place where t was, s was 0. Yeah, you are actually seeing active galactic nuclei or gamma ray bursts. These are examples of now, but redshift of the order of 6 to 7 when these things were much more. Suppose they have done an experiment, observation, we using data from Hubble Space, ESO's 8-meter telescope of certain part of Magellanic stars coming off the main sequence as giant, and this happens only if they are something like 20 giga. Writing a paper in which we want to say that there are indications of such stars. Now, if for standard cosmology whose age is altogether 30 age, no age means there is no finite age.
You can also have blue shifting, right?
Yes, if you look at somewhat at 27 magnitude galaxies, so which spectroscopy of such galaxies is. Thank you.